I hope all of you are doing well today. I am Mr. Ish. Thank you for joining me. I have presented this area formula for regular pentagon using single integrals prior. In the past, I was requested by a viewer to do it by means of double integral, and that's what we are doing here in this video. There will be a bit of repetitive procedures between this and that previous video, but you will see the material in here is interesting. You can start everything here by means of the geometry. You see a regular pentagon sides are equal to A. You have the total internal angles equal to 540 degrees, but each angle, because there are 5 sides for 5 vertices, each of those angles is 108. You can pluck this triangle out and you develop 54, 54, and here a total of 72, which splits into 36, 36. Obviously, you can imagine this right here will be another 54, and that's how you get your 108 degrees. But then you have a continuation here of the pentagon. Our representation here is to develop the area formula of this using double integral, and we will. In the most easy way possible, we have this representing a triangle that you see over here, the side A. There is no trigonometric ratio to help you out over here. The area formula is going to be a squared over 4, and then by means of exact values you end up seeing 25 plus 10 root 5. But when you do this area formula for a regular pentagon by means of integral calculus, this is what you get: 5 tan 54. That's what you get. This 5 tan 54 is equal to exactly that. You can verify it, and I verified it in the previous pentagon video, which I will include the link for in this. But this is the formula we're aiming for, because this is what you're going to get by means of integral calculus. To convert all of this into all of this requires an exact value to come into play. All of that is beyond the scope of this video. Anyhow, our representation is going to be this. Again, there is no trigonometric ratios, but what I'm going to do is go for the simplest procedure using double integrals. So we're looking at this side only, but we have to multiply by times 2 to capture this part I'm missing out, and times 5 because there are 5 triangles you're looking at. And then we have to start by determining what these coordinate pairs are. The coordinates are going to be exactly what you will see right over here, which I will then place over there. Here's my one single triangle. You have the side A. I have a 54 degrees here. I have a 36 over here. I know what this right here is. It's A over 2 because I'm splitting that one side. A over 2 comma 0. That I know. I have to determine this, and I can do it. This right here is height. This here angle is a 54. Tan 54 degrees is equal to your opposite divided by adjacent, h over adjacent, which is going to be a over 2. H is equal to a over 2 tan 54. But I don't want to carry this tan 54 through the entire computation. I'm just doing a simple substitution. Z is equal to tan 54, which we will bring back into our procedure at the end. H is equal to az over 2. That's what I have. This az over 2 will come right over here. 0 comma az over 2. That right there is my coordinate pair. At the end we have to resubstitute z for tan 54. Now for the double integral procedure. Since I'm looking at everything from right over here to here, what will be my integrals? Let's bring the times 2 times 5, that's a times 10. We're going to integrate the dx integral upwards. This point right here is your origin, 0 comma 0. It's going to go straight up, so it's not a problem by any means. It will stay as is. This point over here, this limit, will track the curve, so we need the equation of that line. You can do it easily. Determine the slope. M is equal to az over 2 divided by minus a over 2, and that's going to be a minus z. Y is equal to minus zx plus, and your y-intercept is clearly this. Y is equal to minus zx plus az over 2. Solve for x. X is equal to y minus az over 2 divided by minus z. Reshuffle everything around by means of this. You can say your right boundary curve is equal to az over 2 minus y divided by z. That's going to be this equation right here, and it will take the value of this limit as you're tracking it up. It's taking the equation form here, and it's az over 2 minus y divided by z with respect to dx, which will integrate now with respect to dy from 0 up to this upper limit, az over 2. Remember, z here equals tan 54. Now we integrate this. The antiderivative here is an x. You have the upper limit right here, which is az over 2 minus y divided by z, lower limit 0. And the outcome, as you can imagine, is az over 2 minus y divided by z. This over z can come right out here as a denominator coefficient, because you can literally push it out. It's not a variable. Your variable part is here, which will integrate with respect to y. Everything in terms of the integral will become az over 2. You have a 10 over z, and then this part, the variable component, az over 2 minus y and dy. You just have to integrate this. When you integrate this, you're getting an azy over 2 minus y squared over 2, and then you know you have an az over 2 and a 0. Let's just do this. Put az over 2 in places of y. You don't even need to put 0. You'll get an a squared z squared over 2, which is an over 4, minus all of this into this whole square. You'll have an a squared z squared over 4 over 2, which will be an over a. And as you can see, 10 over z is sitting outside. Do all of this. 4 goes in here 2 times. You'll have a 2a squared z squared minus that is just a single a squared z squared over 8 times 10 over z. Simplify everything. This z will cancel out with this exponent. 2 goes in 8 4 times. 2 goes in 10 5 times. What remains? You have here a squared over 4 times 5z. That's what I have. A squared over 4 5z. Let's resubstitute the z. Our formula will be a squared over 4 5 10 54, which is what I alluded to at the very beginning, and this here is my area formula, and it will be right. And it should be equal to a squared over 4 root 25 plus 10 root 5. That's the geometric formula because you're doing the exact value of tan 54 with a 5, and it's equal to all of this. Either of these formulas is good. This is the formula you're getting through integral calculus. We can just verify that this indeed is equal to that. You do 5 root times 10 plus 25. You're doing all of this square root. I'm getting a 6.88. 5 times tan 54 will be equal to just that. 54 tan times 5, 6.88, minus that saved value coming from here. If they're exactly equal, you'll zero out, and that is exactly what we're doing. We're zeroing it out. So this formula here is good. A squared over 4 5 tan 54 is equal to this formula, the geometric formula for a regular pentagon. And it's normally seen in another way, a squared over 4 root 5 parentheses 5 plus 2 root 5. It also shows up like this. You just distribute it across and you get this 25 plus 10 root 5. Both of these are exactly the same, but you can see it in either of those forms. That right there is the double integral procedure. As you can see, I started with a full triangle, but I'm only focusing on half of it because to deal with only one equation in terms of a limit and going up versus 2, it's difficult. 2, you would have been working with this and that side. Here I'm only working with one side. The other limit remains unaffected. Integral dx with regards to integral dy. A single equation coming into the limit versus 2, and it's easier that way. Times 2 times 5 and a 10. The z coming out also as a constant. Thank you for watching.